All right, welcome back, everyone. Today we'll continue our discussion on the control chart for non-conformities. So far we have talked about control chart for binary quality characteristics. So today now we'll talk about when you can actually count the number of defects on the surface. So this is an example where I'm showing you the defects on a semiconductor wafer. And then we want to construct a control chart that can monitor the number of non-conformities. So let's say if I define X as the number of defects on the semiconductor wafer, and let's say C is the average rate of defects or non-conformities per unit area, then you can see here that X essentially follows a Poisson distribution with parameter C, right? And now this makes it much easier. If I have to construct a control chart for non-conformities, all I need is mu of X and sigma of X, right? And I don't know both of these. Mu of X is C and sigma of X is also C because sigma of X is square root of C because variance of a Poisson is just its rate. And the resulting control chart that we get for the number of non-conformities, it's called a C chart. Okay, so your UCL is C plus 3 square root of C, CL is C, and then LCL is just C minus 3 square root of C. This is the easiest control chart that you might have seen so far. Okay, and then if you don't know C, you can compute C from data, and I'll show an example. C bar is total number of non-conformities divided by number of samples. Okay, and then this will revise your UCL as C bar plus 3 square root of C bar, CL is equal to C bar, and LCL is equal to C bar minus 3 square root of C bar. That gives you the control chart for non-conformities when you don't know C. And a quick example is the next one. Let's say you have sample number running from 1 through 26, and then for each sample you have number of non-conformities. So you can compute C bar from this example. C bar is equal to 21 plus 24 plus 16 plus ... up to 15 divided by 26, and that will give you C bar as 19.85. And then once you have C bar, you can easily compute the control chart. In this case, it will be UCL. This is equal to C bar, which is C bar plus 3 square root of C bar, which is, if you plug in the numbers, you'll get 33.22. Center line is just 19.85, and then LCL is equal to 6.48. Right, that essentially gives you control limits. Okay, now let me talk about a slight modification. Now, many times, instead of having one single, so far we assume that in a C chart, the number of inspection unit is 1. Let me go back and mention this here. We assume that number of inspection units is 1. That's the assumption in the C chart. That might not be true. Your number of inspection units could be more than 1. So in that case, if number of inspection units is more than 1, then your UCL, this is equal to n times C bar, where n is the number of inspection units, 3 square root of n C bar CL is NC bar, and then LCL is NC bar minus 3 square root of NC bar, where N is the number of inspection units. Okay. So this is one example where I want you to keep an eye on if what the question specify. If the question says specifically about number of inspection units, then you have to be careful about that. All right, let's look at an example here. Question says average number of non-conformities per machine when the process is in control is 4. So your C is given to be 4. And it does not talk about the number of inspection units. So we are just going to assume for the time being the number of inspection unit is 1. Find the appropriate 3 sigma control limits. So I can do UCL equals to C plus 3 square root of C, which gives us 10. CL is 4, LCL is equal to 4 minus 3 square root of 4, which is minus 2. Again, keep in mind, we just talked about this. If LCL is negative, ask yourself, can the number of non-conformities be negative? It cannot be negative. So you make it equal to 0, right? And then the second question is, what is the probability of type 1 error? Well, probability of type 1 error is alpha, which is probability that X, which is the number of non-conformities, is greater than equal to UCL, less than equal to LCL, given the process is in control. And then this is equal to 1 minus probability X is less than 10, greater than 0, given the process is in control. I can do a little bit more simplification. I can write this as 1 minus probability of X is less than 10 minus probability X less than equal to 0. And then X, I know, follows Poisson with parameter 4. So you can use your calculator here and you will get an answer of 0.02645. Keep in mind, when you compute the first term probability X less than 10, you have to make sure that in a calculator you put X less than equal to 9, because the cumulative probabilities are not defined for less than, it's always defined for less than equal to. Okay, so be very careful when you're computing these probabilities on a calculator. In fact, I would recommend that you try to compute these probabilities yourself. And then if you have any questions, please reach out to me. Okay, let's do one last one. And this is not very important, but I still like to cover this. This is called a U control chart. This is very similar to what we talked about. Let me write this down. When the number of inspection units is more than 1. If the number of inspection units is more than 1, then you compute a statistic called U, which is equal to total number of non-conformities in N inspection units divided by total number of inspection units, which is N. And then you can construct a U control chart whose UCL is equal to U plus 3 square root of U divided by N. CL is just U, and then LCL is U minus 3 square root of U divided by N. That gives you a U control chart. I hope that makes sense. All right, there's one last question. Let's try to solve this. Question says a control chart for non-conformities is maintained on a process producing desk calculators. The inspection unit is defined as 2 calculators, and the average number of non-conformities per machine when the process is in control is estimated to be 2. So number of inspection units which is n is equal to 2, and then you're given c, which is equal to also 2, right? Since we have c available, we have n available, we are going to use an NC control chart in this case. The question says find appropriate 3 sigma control limits for this size inspection unit. So for the first problem, we can construct an NC control chart, and your UCL will be NC plus 3 square root of NC. If you plug in the numbers, you'll get 10, CL is 4, and LCL is, again, 4 minus 6, which is -2, so you make it 0. So you've got that. And then the other question is, what is the probability of type 1 error for this control chart? It's very similar to the question that we just did a few minutes ago. In fact, alpha is equal to probability that NC is greater than equal to UCL, less than equal to LCL, given the process is in control. This is equal to probability NC. Actually, let's say this is equal to 1 minus probability NC less than 10, greater than 0, given in control. And this is exactly the same problem that we have just done a few minutes ago. This is the same problem. X follows a Poisson distribution in that case. NC follows a Poisson distribution in this case with parameter 4. So in fact, if you compute the exact numbers at the end of the day, you should get a pretty similar or exactly the same number. So please try yourself, and if you see any issues, please let me know. All right, thank you very much, and let me stop here. I think the answer to the last question should be 0.00, and I might be mistaken here. It should be 0.02645. Let me quickly do this computation, and maybe I can update here right away. Sorry, I've not computed this number beforehand, so give me 1 second. So your final answer should be, yes, it should be 0.02645, which we calculated earlier. All right.